everyone. This is the final lecture of the final week, in fact the final lecture of this course. You can recall that in this week we were working on a machine learning application to implement ridge regression using optimization algorithms. So, in the previous lecture we worked out the constrained optimization version of the ridge regression method, right. So, in this lecture we will start with the unconstrained version. Okay. So, if you look at the screen, right. So, please note that in the constrained version we had an S, and I told you that there will be a mu corresponding to each value of S, right. So, and what is that mu? It is the mu star that we get when we solve the Lagrangian of this particular problem, right. So, I mean when you solve this constraint problem by hand, we have this problem L of beta hat mu equal to the objective function plus mu into the constraint equation, right. So, yeah, when we solve for this problem, we not only solve for beta hat, but we also solve for mu, right. So, let us say the optimal value is mu star, right. So, the solution of the constraint problem and the solution of the unconstrained problem are the same if we use the mu star that we obtained from the constrained version. Okay. So, that was one of the reasons why I solved the constraint problem first. Okay. So, now when we want to solve for the unconstrained problem, right. So, I mean we will take mu star, right, that we obtained from the constraint problem. Okay. Recall that in one of the previous lectures we actually found the value of mu star as well for each of the values of S, right. So, for point 1 it was the equivalent mu star was 28,771.69, and for point 2 it was 16,834.778 and so on, right. So, and yeah, you can also see that for 256 it was 0, right. So, that the reason is that the constraint was not active, right. So, for active constraints you can recall that Lagrange multiplier will be 0, right. So, when I give 256, right, not just 256, if you give any value greater than this, right. So, you can try it in home, right. You give S that is greater than this, right, you will certainly get your mu star to be 0, and the sum of squares of the test errors, right. So, that will be the same 4016.74. Okay. Anyway, so what we are going to do is we are going to use this value of mu star, okay, and solve for the unconstrained problem that is boxed below in the screen. Okay. So, let us do that. We will only have f of x, right. So, yeah, but it is slightly different from this, but given that we will use this. Okay. So, yeah, I will also write the text which is ridge regression unconstrained, right. Okay. So, I think I should write a name here as well, let me do that. So, this is ridge regression using penalty method. Okay. All right. Yeah. So, fine, this is the first part, the sum of squares of the errors, right. So, with this we should add mu into, so this is yeah, x of 1 dot x of 1, right. So, all right, and we will define the gradient and the Hessian as well. Okay. So, yeah, this is something that we have defined in other places as well, right. Yes. So, this is exactly the gradient of f of x, I mean the gradient of this part, right. and for this part we need the gradient of g that we defined here. Okay. So, let us take that from here. Okay. Yeah, it is this part. Okay. And we will also define the Hessian, since yeah. So, we will first solve it with Newton's method. Okay. So, this is yeah, at least the Hessian of this is 2 A transpose A. Sorry, the Hessian of this is 2 A transpose A, and for this we will have the oh yeah, I missed the mu into, sorry, yeah. For this we will have what we defined here as Hessian, right. Yeah, this part NP dot diag into all this part, right. Okay. So, fine, yeah, we have defined f of x and its gradient and Hessian. Okay. So, and yes, we will also initialize the values, maybe since we are only going to use Newton's method, we will start with Newton's method, we can possibly think about the other methods a little later. Okay. So, yes, this is Newton's method. So, yeah, this is yeah, for general functions. So, it is this. Okay. So, we will take this. So, the initial point is we have defined all ones, right. So, we will start with that, and yeah, print is all not required. Okay. I think this is a slightly different method, but nevertheless we can change this very easily. Yeah. Okay. So, let us take this particular method, and after finishing we will print the value of k. I mean, we will see how many iterations it took and the test error which we have here. Okay. All right. Yes, we can run the code. Oh, okay. Since we are starting afresh, I need to import NumPy. Okay. Okay. So, fine. I think we will have to run the xtrain and all of this. So, let us run this once, so that all the yes. So, the values of xtrain, xtest, ytrain, ytest a, all of that is defined, right. So, yeah, I have run this now, and now we will yeah, run this. Okay. Yes, I should have defined the value of mu. So, though I mentioned it in the beginning, right. Yes. So, this is the value of mu. So, let us take that. Yes. Okay. It says the size is different from 14. Okay. So, I suppose the problem is with grad. So, let us debug this straight away. Yeah. So, let us print the shape of h of x and the shape of grad of x. Okay. That might be of help to understand. Oh, okay. So, it is 1 comma 14 instead of just 14. Okay. So, I think I can modify this to be this way, the following. Yeah. Yeah, I suppose now it may work. Yes, done. Okay. Yes, now we can remove this print. All right. Yes. So, good. You can see that it just took 2 steps. Okay. So, if you recall the constrained version which we solved in the last class, we were struggling with a lot of steps and so on, but note that here we just got the answer in 2 steps. Okay. This should actually be not be surprising, okay, because the reason is that this is actually a quadratic function, right. So, Newton's method solves quadratic function in a trice, isn't it? So, that is the reason. Okay. Yeah, if it was so the problem is so big, so large and all that, yes, that is all correct. Okay. But since the form of the objective function is just quadratic, right. So, Newton's method solves this in a trice, and that is what you have observed it here. Okay. And yes, you can also observe that the answer is exactly the same, 1639.04, right. Yeah. So, that is what you had here as well. Okay. So, yeah, we are just using the algorithms that we have learnt to solve this problem, the ridge regression problem, where you get the solution beta naught hat, beta 1 hat, dot dot dot, beta p hat, right. So, yes, so this is using the Newton's method, okay. And so you can also solve using other methods. We will just solve using one other method, okay, which is BFGS method, okay. For the other ones, I think you can repeat the code and I mean find the solutions yourself, okay. So, yeah, this part will remain the same, okay. And we will now move to BFGS algorithm, okay. Okay. So, yes, quasi Newton method, and yes, you have the BFGS algorithm here, okay. So, we will start from this, and yeah, so we can complete it here. And actually this is not just for BFGS, it is actually the, you can say, the Broyden family of algorithms, where we have B equal to 0.2 into DFP plus 0.8 into BFGS. So, you can recall the phi into DFP plus 1 minus phi into BFGS, where phi could take any value between 0 and 1, okay. So, here we have taken 0.2, okay. So, let us see if this needs a change. Yes, so this is needs to be yeah, I mean I do not need to print the values, and so this is actually 14, okay. Yeah, and I think yes, so this has to be h of x, okay. I suppose yes, I think everything else is fine, okay. So, yeah, let us check how long this takes. Oh, okay, I did not print the answer here. So, yes, so yeah, okay. So, this has taken 14 iterations, and you can see that it has given the same answer as well, okay. You can try this with the other algorithms as well, say conjugate gradient algorithm, and also gradient descent algorithm. And so, you will also see that when you try gradient descent, okay, I mean the solution will actually take quite a long time to complete, okay. So, like say millions of iterations, okay. So, the reason is, I mean, if you recall what we learnt in 4th week or 5th week, I suppose, okay. So, you can recall that if the eigenvalues of the Hessian matrix are not close enough to each other, right, the ratio of the highest eigenvalue to the lowest eigenvalue is not close to 1, okay. In that case, the gradient descent actually takes a long time, right. So, note that the Hessian here is huge, right. So, the function itself has, I mean 400 data points, right. So, the objective function itself is huge, and the Hessian is haywire, right. So, of course, the ratio is would be far off from 1, okay. So, I mean please do not expect the all the eigenvalues will be close enough, right. So, in fact the highest eigenvalue and the lowest eigenvalue will be as far as possible, right. So, you can try it in your home using gradient descent, okay, and you will see that the number of iterations that you need runs in millions, okay, like 2 million, 3 million, something as large as that, okay. So, that is why I mean we try to avoid gradient descent as much as possible, right. Gradient descent, as you all know, is the simplest method, okay. I mean it just goes through the negative of the gradient, the direction chosen is just the negative of the gradient, right. But yeah, I mean when the Hessian is does not satisfy the desirable properties, right, it turns out that yeah, the method is just very slow, Okay. So, you just note this, I mean problem where Newton's method can find the answer in 2 steps, where the Broyden family can find the answer in 14 steps, right. So, you are the gradient descent is taking millions of steps, right. So, yeah, that is something we try to avoid. Okay. So, yeah, this I mean completes the application, right. So, we have actually discussed, we have taken an application and have used many of the algorithms that we discussed throughout this course and have solved for this ridge regression problem, right. Before completing this application, right. So, I want to tell you 2 things. Okay. The first one is, so given that this is a machine learning problem, right, you might actually be asking if I mean people who are actually implementing ridge regression, do they actually implement all of these algorithms, I mean the whatever Newton's method or the penalty method or augmented Lagrangian method or whatever, right. So, of course, I mean if what you want to do is just to solve this ridge regression problem, okay, I mean Python has actually given a library itself to solve all of these problems, in the sense that I mean whatever we are doing here, right. So, it is actually implemented in as a subroutine and given as an inbuilt command to us. Okay. So, I would like to let you know about that particular command. Okay. So, that again uses a different library. So, we have only used NumPy and maybe Matplotlib and Pandas. Pandas, so I did not teach you, I mean it was just to I mean input the data, right. So, we have a library called scikit-learn. Okay. So, yeah, you might search for this in the internet, right. So, if you have come thus far, you can do all of this, right. So, but I will just tell you the library and the command, okay, so that you I mean get to know what I mean how you would do ridge regression. Okay. So, this is a library called sklearn. Okay. So, its full form is scikit-learn. Okay. I mean I will just write this is scikit-learn. Okay. So, in case you want to look it up, you can look it up for sklearn. Okay. So, in this we are actually going to choose the sub library called linear underscore model. Okay. So, we will take this as skllm. So, this is just what I am naming, you can name it as anything you want. So, this is skl scikit-learn linear model, that is why I am calling it skllm. Okay. So, in this, okay, I should use a command called ridge. Okay. So, yeah, it gives a thing, right. This is called, so note that the ridge is with capital R. Okay. So, if you put small r, it will not work. Okay. And you have to give the mu parameter and not the s parameter that we did in constraint optimization. Okay. So, the new mu parameter, if you can recall, is this 16,834.778 or whatever. Okay. So, yeah, use this. Okay. And so, you can call this maybe as CLF. Okay. I mean, so CLF is for classifier. Okay. So, or for regression you can call it REG or something, it is okay. Okay. So, I mean this is the model that we are after. Okay. And what you want to do is to fit x train comma y train, right. Yeah. So, the feature vectors is given in x train and the labels are given in y train, right. So, this will be 506 cross 13 matrix and this is 506 length vector. Okay. So, the CLF is I mean fit with x train and y train. Okay. Now, using this we will actually print. So, after you fit, I mean, so what this command does is it computes the values of beta naught hat, beta 1 hat, dot 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 beta p hat. Okay. So, now if you want to predict for a test vector, you have to use CLF dot predict. Okay. So, we will predict for all x test. Okay. So, you will have a 106 dimensional vector. Okay. But I mean rather than this, we are actually interested in a test error, right. So, you have to do this. Okay. So, find the difference between this y test minus CLF dot predict of x test, okay, and take the square. Okay. You take the difference and take the square and then I mean sum it over. Okay. So, we will try to print this. Okay. Yeah, so we can straight away see that the answer is 1639.038. Okay. So, right, I mean, so in case your objective is just to solve a ridge regression problem. Okay. So, I mean you do not need to go via the optimization way. Okay. I mean, but so in case you are asking, then I mean why at all did we learn this application and so on. Okay. So, in case you are actually learning more sophisticated machine learning, right. So, you will actually see that you cannot just use the inbuilt commands for all the methods that you are learning. Okay. For example, say neural networks. Okay. So, the TensorFlow and PyTorch libraries that use to construct a neural network. Okay. So, they have a lot of limitations in the sense you want to construct a more sophisticated neural network. Okay. Or with a more sophisticated loss functions. So, there are certain loss functions for which your inbuilt commands in Python will be of help. Okay. If not, I mean note that you might have to use optimization algorithms to actually construct the loss function and I mean construct an answer from them. Okay. So, that is where actually the algorithms that we learned will be useful. Okay. And finally, so I said that optimization algorithms will be useful, right. So, the final question that we need to answer is maybe which of these algorithms are used in machine learning applications, right. So, we have learnt quite a lot of methods starting from gradient descent, conjugate gradient, Newton's method, quasi-Newton's method to the ones in constraint optimization for linear and non-linear programming problems, right. So, which of these is used in machine learning applications, right. The answer unfortunately is that none of these are actually used for machine learning. Okay. In fact, to be precise, okay, the algorithms that are used for machine learning applications, okay, they are actually called stochastic optimization algorithms. Okay. Those are actually more advanced than what we have learnt until now. Okay. So, you can say that what we have learnt is to an extent basic algorithms. Okay. So, if you are looking for the names of those algorithms, okay, so you must be looking at, so I will just write other algorithms, other advanced algorithms, so used in ML. Okay. So, three major algorithms that are used for ML are, one is called the stochastic gradient descent. Okay. So, yeah, you will see the name SGD very often. Okay. The other one is called LBFGS, okay, and the other one is called the Adams optimizer. Okay. So, stochastic gradient descent will be easy if you know what gradient descent is. Okay. So, it is, you can say, a slightly advanced version of or rather the stochastic version of gradient descent. Okay. And LBFGS is you can say an advanced version of BFGS itself. Okay. And Adams optimizer is a slightly different kind of an algorithm. Okay. So, these are the three important optimization algorithms that are useful in machine learning applications. Okay. And I mean, so if you want to learn them, we will have to possibly take up a different course. Okay. Yeah, I might offer that sometime later. Okay. And yeah, I would like to invite you all who have completed this course to that particular course as well. Okay. Fine. So, I would like to give you a final note, okay, about Python codes for optimization. Okay. So, what all we have learnt is step by step procedure, right. That is, I mean, when you have an optimization problem to solve, so I have given some routines. So, you just put them in and solve it, right. In fact, so as I said for ridge regression, right. So, we solved ridge regression using optimization algorithm from scratch, right. So, you have a command which actually implements all of this and gives you the answer, right. In a similar way, you have certain commands in Python which actually solve an optimization problem. Okay. So, I will just give you those commands, okay, and solve one constrained and one unconstrained problem. Okay. We will end the course with that. Okay. So, I mean, suppose you just want to solve an optimization problem using Python. Okay. You can just use these commands. Okay. So, I just want to let you know about that, and I mean, in case you want to learn more about this, you can read about it. Okay. So, this is actually from another library called scipy.optimize. Okay. So, also give that command. Okay. So, this is scipy is the basic library and optimize is a sub library. Okay. So, I am giving this command, I mean, I am defining this as SPO. Okay. Again, you can define it whatever you want. Okay. And suppose you just want to minimize this function. Okay. So, I have defined f anyway, right. So, let us say you want to just, you can define an f of x and solve this unconstrained problem. Okay. So, let us just do that. So, what you need to do is define the result as that is scipy.optimize.minimize f comma the initial point we know is all ones, 14 ones, right. Okay. So, we will print the value of x that we want, right, that is the beta value. We have not printed this anywhere until now, but yes. So, this is the beta value, okay, that is fine, but we are more interested in the test error, right. So, we will again take this, okay, but just that instead of x we need to write res dot x, that is the difference. Okay. Yeah, you can see that it is again the same 1639.03. Okay. So, yeah, that is I mean, it is as simple as that to minimize an unconstrained optimization function. So, but if you want to do a constrained optimization function, okay, so yeah, you also have to define a constraint. Okay. So, I will just do that quickly and end the course. Okay. So, yeah, I mean, let us actually take this particular problem. So, this is something that we defined in the beginning. Okay. So, we will minimize minus x1 x2, right. So, this is the consumer utility maximization problem. So, we are maximizing x1 x2. So, subject to constraint that p1 x1 plus p2 x2 is less than or equal to w. So, as a simple method we will write x1 plus x2 less than or equal to w, okay, and x1 greater than or equal to 0, x2 greater than or equal to 0. Okay. So, the answer is actually half, sorry, yeah, this is 1, let us say, yeah. So, the answer is actually half and half. Okay. So, since I just want to give you an example for constrained optimization as well, I am doing this. Okay. So, we will define f of x to be minus x of 0 into x of 1, okay, and g of x to have all the constraints, right. So, this is x of 0 plus x of 1 minus 1 minus x of 0 and minus x of 1. Okay. So, we will write an np dot array. Yes. So, and you have to define the bounds as well. Okay. So, this is something new. Okay. So, I am defining yeah. So, this is nonlinear constraint, okay, SPO dot nonlinear constraint. So, for G, okay. So, note that, so this is all less than or equal to 0, right. So, the left hand limit is minus infinity and the right hand limit is 0, okay. So, you need this infinity into ones of 3 and this is just zeros of 3, okay. And yeah, so you will just have this res equal to SPO dot minimize of f. So, you need an initial point, we will just put it as 0, okay, np dot zeros of 2, and you need to say that the constraints are in place. So, you just say CNS, okay, and we will print res dot x as the answer. Okay. So, I had to mention this as constraints. So, yeah, it's a small error that I did. So, yeah, I mentioned this as the CNS what you have written is actually the constraints. Okay. So, let us do that. We will using zeros, I think there is a problem because of the objective function, right. So, we will use different initial point, right. So, maybe some 0.1 comma 0.2, okay, and yes. So, you can see that the answer is half comma half, right. So, you can use something else as well, say yeah, let us say 0.01 comma 0.02 as well, okay, and yeah, you can see that the answer is half comma half as well, right. So, all right, yeah. So, this is again inbuilt function that I wanted to discuss before finishing the course, okay. So, but if you are asking how the computer solves this, right. So, it uses the algorithms that we discussed throughout this course, okay. So, who would like to do research on this, okay. I would welcome you to actually improve these algorithms, okay. So, there are certain algorithms that have been implemented. You can use these algorithms or in fact design more efficient algorithms which can give the answers even faster, okay. So, yeah, this with this we actually would like to end the course, and I would like to thank you all the students who have come thus far, okay. I hope yeah, the world of optimization algorithms was very interesting, okay. Let us meet again in some other course which I might offer sometime later. Thank you all.